We're going to be looking now at trees. Trees are a special kind of graph which show up in many applications. So consider the graph on the left. Kind of looks like a tree. So our formal definition of a tree is that it's an undirected graph which is connected and has no cycles. So what does that mean? Well, recall that a cycle is a graph that looks like a circle. So it starts and ends at the same point without repeats. And you can see an example of a cycle in the lower right-hand corner. Note that even though I called it circular, it may not look like a circle. The circle reference comes from the fact that if you start at a point, let's say here, and follow around the graph, you never repeat anything and eventually come back to where you start. You can also redraw this graph to make it look more circular instead. Looking at the tree on the left, it does not have any cycles. If you pick somewhere to start and you start moving around, you can never get back to where you started without repeating something. The other part of the definition was connected, so that means that you need to be able to draw the tree without having separate pieces. So let's look at a few examples here. We want to see which of these graphs are trees and which are not. So start with graph A on the left. Recall that a tree is connected. This is connected. You can move from anywhere in the figure. And a tree has no cycles. Unfortunately, this does have a cycle. It has a cycle right along here. And so this is not a tree. Looking at B, it is connected, meaning that you can get from anywhere to anywhere else. For example, I could walk between those 2 points. And there are no cycles. If you pick a starting point and you start walking around, you can never get back to where you started without repeating something. So far we have not a tree, and then yes, this is a tree. And then look at graph C. Well, this one has no cycles. If you pick somewhere to start and you move around, you'll never get back to where you started without repeating something. However, it is not connected. If you look at the top and then you look at the bottom, it is not possible to get from A to D by just following these edges. Now let's look at some properties of trees. So the first property of trees we're going to look at relates to the number of edges and vertices, or how they're related to each other. So consider the little tree on the left. Note this is a tree because it is connected. You can walk around it and get anywhere you want. And it has no cycles. So let's suppose I start at vertex A, and I want to count the number of vertices. So I have one vertex so far. Then I'm going to add edges one at a time. For example, I add this edge. Now what happened when I added that edge? It added one edge and it added one vertex. So plus one vertices and then plus one for edges. Then let's continue this process. I'll add another edge. Well, again, I added one to the number of vertices and one to the number of edges. Repeat. Again, one to the number of vertices, one to the number of edges. And finally, the last one, one to the number of vertices, one to the number of edges. We'll notice that when I did this process, every time I added an edge, I also added a vertex. And so that shows us that in total, we have that first vertex A, and then exactly the number of edges after that. So from this, we can conclude that in a tree, the number of vertices is 1 plus the number of edges. So this is one of the key properties of trees. If you have a graph which does not match this formula, then you know it cannot be a tree. Here's another property of trees. The definition said there are no cycles. So here's a tree we've looked at a few times that has no cycles. However, if I add an edge anywhere in this graph, for example, across there, then it will create a cycle. Or maybe I try down below. Well, that creates a cycle too. And so this shows us that when you add even one edge to a tree, you get a cycle. So from this, we see two interesting properties of trees. First, the number of vertices is 1 plus the number of edges. Second, if you connect any 2 points, you get a cycle. And these are actually fundamental properties of trees. So if you consider a connected graph that has the property that adding any edge will give you a cycle, then it is a tree. And if you consider a connected graph that has the property that the number of vertices is 1 plus the number of edges, then likewise, you again get a tree. You can find additional properties of trees if you look online, but these are perhaps the two that are the most useful. Let's try out those properties on an example. Consider the following tree. We know this is a tree because it is connected. If you pick any 2 points, you can get between them by following edges. And it has no cycles because if you pick a starting point and start wandering around, you can never get back without repeating something. At this point, I would have to backtrack. So the first property of trees was that if it was connected, it is, and the number of vertices is 1 plus the number of edges. So let's do this, has 1, 2, 3, 4, 5, 6 vertices. The number of edges here is 1, 2, 3, 4, 5. Then it is a tree. Well, indeed, connected, and it satisfies that property. So this is a tree. The other property that is special about trees that we mentioned was that if you add an edge anywhere in this graph, you will create a cycle. So let's try adding one. Perhaps I add this edge. That looks like it shouldn't be a cycle. But notice that it does, right around the outside here. So that one edge created a cycle. Well, maybe that was just a fluke. Let's try a different one. Let's see, we can take our highlighting and how about add this edge? Well, again, we got a cycle. So that didn't trick anything. Well, maybe I just need to be a little more circumspect. Well, if I do that, again, I get a cycle. So it looks like every way I try to add a single edge, I end up with a cycle. So adding any edge gives a cycle. And again, it needs to be connected.